Why should you dive in? Discover the mysteries of the cosmos. The important thing is not to stop questioning. Curiosity has its own reason for existence. Albert Einstein. Have you ever gazed at a starry night sky and wondered about the mysteries of the universe? What are black holes, and how do they work? How did the universe begin, and what will it look like in the future? These profound questions have intrigued humanity for centuries, and A Brief History of Time by Stephen Hawking offers a window into the answers. In this remarkable book, Hawking deciphers the complex laws that govern our universe in language that is accessible to everyone, even those without a scientific background. By delving into topics like the Big Bang, black holes, and the nature of time, he helps us understand why the universe exists, how it started, and what its future might hold. The journey begins with the Big Bang, the cataclysmic event that gave birth to the universe. Hawking explains how this singular moment set everything into motion, leading to the formation of galaxies, stars, and planets. He also addresses the concept of time, exploring questions like how fast is time going? And how do we know it's going forwards? Black holes, one of the most fascinating phenomena in the cosmos, are also demystified. Hawking describes these cosmic vacuum cleaners that can suck in everything around them, including light. Yet, he also reveals the groundbreaking idea that black holes might emit radiation and eventually evaporate over time, a theory now known as Hawking radiation. Moreover, Hawking touches on the ultimate fate of the universe. Will it continue to expand indefinitely, or will it collapse back into a singularity? Through these explorations, he provides insights into the possible end scenarios for our cosmos, leaving us to ponder our place in the grand scheme of things. In the final analysis, A Brief History of Time doesn't just inform us about the universe, it transforms our perspective on it. By presenting the intricate workings of the cosmos in a comprehensible manner, Hawking invites us to see the night sky not just as a scattering of stars, but as a vast, interconnected tapestry governed by the laws of physics. So, as you turn the pages of this book, prepare to embark on a journey that will expand your mind and ignite your curiosity. As Carl Sagan once said, somewhere, something incredible is waiting to be known. Dive into A Brief History of Time, and you might just find that incredible something you've been looking for. If you find this exploration enlightening, don't forget to like, share, and subscribe to our channel to spread the wonder of science and discovery. About the author. Stephen Hawking, Ph.D., 1942 to 2018, was a renowned theoretical physicist and cosmologist, celebrated for his groundbreaking work on Hawking radiation and the Penrose-Hawking theorems. Serving as the Lucasian Professor of Mathematics at the University of Cambridge from 1979 to 2009, Hawking made significant contributions to our understanding of the universe. His numerous accolades include the Presidential Medal of Freedom, an honorary fellowship at the Royal Society of Arts, and lifetime membership in the Pontifical Academy of Sciences. Theories based on past observations can help predict the future. You've likely heard of the theory of gravity or the theory of relativity, but have you ever paused to consider what we truly mean when we talk about theories? A theory, at its core, is a model that accurately explains a large group of observations. Scientists collect data from experiments and observations, using this information to develop explanations of how and why phenomena occur. For instance, Isaac Newton developed the theory of gravity after observing many phenomena, from apples falling from trees to the movements of planets. Using the data he collected, he was able to describe gravity in a comprehensive theory. Theories offer two significant benefits. First, they enable scientists to make precise predictions about future events. For example, Newton's theory of gravity allows scientists to predict the future movements of objects like planets. If you want to know where Mars will be 6 months from now, you can accurately predict this using the theory of gravity. Second, theories are always disprovable, meaning they are open to revision if new evidence that doesn't fit the theory is found. For instance, people once believed that everything in the universe revolved around the Earth. Galileo disproved this theory when he observed moons orbiting Jupiter, showing that not everything orbits the Earth. In essence, a single future observation can always invalidate a theory, no matter how reliable it seems at the moment. This means theories can never be proven correct, making science a constantly evolving process. Isaac Newton's revolutionary laws of motion. In the 1600s, Isaac Newton fundamentally changed our understanding of how objects move. Before Newton, the prevailing belief was that an object's natural state was one of absolute rest, meaning if no force acted upon it, the object would remain completely still. Newton thoroughly disproved this long-held belief and introduced a theory stating that all objects in the universe are in constant motion. He determined this through his discovery that planets and stars are continuously moving relative to each other. For instance, Earth is constantly orbiting the Sun, and the entire solar system is rotating around the galaxy, meaning nothing is ever truly still. To describe how all objects in the universe move, Newton developed three fundamental laws. Newton's first law states that all objects will continue moving in a straight line unless acted upon by another force. This was demonstrated in an experiment by Galileo, in which he rolled balls down a slope. With gravity as the only force acting on the balls, they continued to roll in a straight line. Newton's second law states that an object will accelerate at a rate proportional to the force acting on it. For example, a car with a more powerful engine will accelerate faster than one with a less powerful engine. This law also states that the greater the body's mass, the less a given force affects its motion. For instance, two cars with the same engine will accelerate differently if one is heavier, with the heavier car taking longer to speed up. Newton's third law describes gravity, stating that all bodies in the universe attract each other with a force proportional to the mass of each object. This means that if you double the mass of one object, the gravitational force between it and another object will be twice as great. If you double one object's mass and triple the other, the gravitational force will be 6 times as great. Through these laws, Newton revolutionized our understanding of motion, demonstrating that instead of being static, objects are always in a state of constant movement, influenced by various forces acting upon them. The revolutionary implications of the constant speed of light. Isaac Newton's theory eliminated the notion of absolute rest and introduced the idea that an object's movement is relative to another object's movement. This relativity extended to speed as well. For instance, if you're reading a book on a train traveling at 100 miles per hour, a bystander watching the train would see you traveling at 100 miles per hour, but relative to the book, your speed is 0 miles per hour. Thus, your speed is relative to another object. However, Newton's theory encountered a significant challenge: the speed of light. Unlike other speeds, the speed of light is constant and not relative. It remains 186,000 miles per second, regardless of the observer speed. Whether a train is moving toward a beam of light at 100 miles per hour or is stationary, the speed of light remains the same. This constancy presented a problem for Newton's theory. How could the speed of something be constant irrespective of the observer's motion? This question was pivotal in the early 20th century, leading Albert Einstein to develop his groundbreaking theory of relativity. Einstein's theory fundamentally changed our understanding of space and time, demonstrating that the laws of physics are the same for all non-accelerating observers and that the speed of light within a vacuum is the same no matter the speed at which an observer travels. This revelation had profound implications, showing that space and time are intertwined in a four-dimensional space-time continuum, and it highlighted the limitations of Newton's framework. In essence, Einstein's work explained that measurements of time and space are affected by the relative motion of observers. His theory showed that as objects move closer to the speed of light, time slows down for them relative to a stationary observer, and lengths contract in the direction of motion. This was a radical departure from the classical mechanics of Newton, which assumed time and space were absolute and unaffected by an observer's motion. The constancy of the speed of light thus not only challenged existing theories but also paved the way for a deeper understanding of the universe, influencing subsequent scientific research and technological advancements. It underscored the need to consider the observer's frame of reference when measuring speed, time, and distance, leading to a more comprehensive view of the physical world. The groundbreaking implications of Einstein's theory of relativity. The constancy of the speed of light posed a significant challenge to Newton's theory, which relied on the idea that speed is relative. To address this, scientists needed a new model that could accommodate the unchanging speed of light. Enter Albert Einstein and his revolutionary theory of relativity. Einstein's theory of relativity fundamentally altered our understanding of physics by stating that the laws of science are the same for all observers in uniform motion. This means that regardless of an observer's speed, the speed of light remains constant. At first glance, this concept may seem straightforward, but it leads to a profound and counterintuitive conclusion: time itself is relative. In essence, the theory of relativity asserts that because the speed of light is constant for all observers, those traveling at different speeds will perceive time differently. For instance, imagine a flash of light is sent to two observers, one moving towards the light and the other moving away from it at a faster speed. Despite their differing velocities and directions, both observers would measure the same speed for the light. This phenomenon means that each observer experiences the light flash event as occurring at different times. This is because time is calculated by dividing the distance traveled by an object's speed. While the speed of light remains unchanged, The distances traveled by each observer differ, making time relative to each observer. To illustrate, if both observers carried clocks to record the emission of the light pulse, their clocks would show different times for the same event. This leads to the mind-bending realization that both observers are correct from their own perspectives. Time is not absolute but relative to each individual's frame of reference. Einstein's theory of relativity has profound implications, demonstrating that our intuitive understanding of time and space is limited. By revealing that time can vary depending on the observer's motion, Einstein's work reshaped our comprehension of the universe, paving the way for advancements in physics and technology. It underscores that in the realm of high velocities and cosmic scales, our everyday experiences of time and space do not apply, requiring us to adopt a more complex and nuanced view of reality. Understanding quantum states and the uncertainty principle. All matter consists of particles such as electrons and photons, which scientists strive to measure to better understand the universe. However, these particles exhibit a peculiar behavior when subjected to measurement. The more precisely one attempts to measure a particle's position, the more uncertain its speed becomes, and vice versa. This phenomenon, known as the uncertainty principle, was first discovered in the 1920s. Due to the uncertainty principle, scientists needed alternative methods to study particles, leading to the concept of the quantum state. A quantum state represents the various possible positions and speeds of a particle, combining these probabilities into a single framework. Since pinpointing a particle's exact position or velocity is impossible, scientists consider the range of probable locations and velocities a particle might have. To understand these probabilities, scientists treat particles as if they are waves. This wave-like behavior means that particles can be thought of as existing in multiple positions simultaneously, creating a continuous, oscillating pattern similar to a vibrating string. When a string vibrates, it forms peaks and troughs. Similarly, a particle's path can be visualized as a series of overlapping waves. This wave model helps scientists determine the most likely positions of a particle. The areas where the peaks and troughs of these waves align, or interfere constructively, indicate the highest probability of the particle's location. Conversely, where the waves do not align, or interfere destructively, the probability is lower. This concept, known as interference, is crucial for identifying the most probable positions and velocities of particles. By adopting the wave-like view of particles, scientists can make more accurate predictions about their behavior. This approach not only accommodates the uncertainty inherent in quantum mechanics but also provides a clearer picture of the subatomic world. Through this method, researchers continue to unravel the complexities of particle behavior, contributing to our broader understanding of the universe. Gravity and the curvature of spacetime. When we observe the world, we see it in three dimensions: height, width, and depth. However, there is a fourth dimension that we can't directly perceive: time. This fourth dimension combines with the other three to form a four-dimensional construct known as spacetime. Scientists utilize this four-dimensional model to describe events in the universe. An event is defined as something that happens at a specific location in space and at a particular time. Therefore, when calculating an event's position, scientists include three spatial coordinates and a fourth temporal coordinate to account for time. Considering time is crucial because, according to the theory of relativity, time is relative and can vary depending on the observer's speed and gravitational field. This relativity of time plays a significant role in accurately describing the nature of events in the universe. A fascinating consequence of combining space and time is its impact on our understanding of gravity. Gravity, according to Einstein's theory, is the result of massive objects curving spacetime. Large masses, like the Sun, create distortions in the fabric of spacetime. Imagine spacetime as a stretched-out blanket held in the air. If you place a heavy object, like a bowling ball, in the center, it will cause the blanket to curve around it. This is analogous to how massive objects distort spacetime. Smaller objects, like planets or marbles on the blanket, follow these curves, resulting in what we perceive as gravitational attraction. Objects follow these curves because they move along the shortest path between 2 points in curved spacetime, which is often a circular or elliptical orbit around the larger mass. This phenomenon explains why planets orbit stars and why satellites orbit planets. Just as a marble rolls along the curved path created by a bowling ball on a blanket, celestial bodies move along the curves in space-time created by massive objects. When a star with a very high mass dies, it collapses into a singularity called a black hole. When a massive star exhausts its nuclear fuel, its fate hinges on its size. For the most massive stars, those many times larger than our Sun, The culmination of their life is a dramatic collapse into what is known as a black hole. Throughout their stellar life cycles, these giants sustain themselves by generating immense energy through nuclear fusion. This energy production counteracts the inward pull of gravity, maintaining the star's equilibrium. However, once these stars deplete their fuel, they lose the energy needed to resist gravity's relentless grasp. Without the outward pressure from nuclear reactions, gravity causes the star's core to collapse inward. This collapse intensifies until the core collapses into an infinitely dense point known as a singularity. This singularity marks the center of the black hole. The formation of a black hole doesn't stop at the singularity alone. Surrounding the singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. The event horizon is defined by the point at which the gravitational pull becomes so strong that the escape velocity exceeds the speed of light. Once anything crosses this boundary, it is drawn inexorably toward the singularity and can never return. Detecting black holes is a complex endeavor because they do not emit light themselves and absorb all light and matter that crosses their event horizon. Scientists employ indirect methods to identify them. They observe the gravitational effects these massive objects have on nearby stars and gas clouds. They also look for the radiation emitted when matter spirals into a black hole, generating X-rays and other forms of radiation that can be detected from Earth. In the center of our Milky Way galaxy, astronomers have observed a powerful source of radio waves and infrared radiation, believed to originate from a supermassive black hole. These observations provide compelling evidence for the existence of these cosmic phenomena, which play a crucial role in shaping galaxies and influencing the evolution of the universe itself. Understanding black holes not only sheds light on the extreme physics at play in the universe but also deepens our appreciation of the interconnectedness of celestial bodies and the profound impact of gravity on cosmic scales. Each discovery about black holes brings us closer to unraveling some of the universe's most profound mysteries and refining our understanding of its fundamental laws. Black holes, enigmatic cosmic entities known for their intense gravitational pull, also possess a surprising ability: they emit radiation. This phenomenon, known as Hawking radiation, challenges the conventional understanding that nothing, not even light, can escape a black hole's grasp once it crosses its event horizon. According to the laws of thermodynamics, specifically the second law, entropy, measuring the amount of disorder in a system, always tends to increase. This law implies that any closed system will naturally move towards greater disorder over time. For black holes, which accumulate mass and energy through gravitational attraction, this poses a theoretical challenge. If they only absorbed energy and matter without emitting anything, they would violate this fundamental law. Stephen Hawking proposed a groundbreaking solution to this paradox in the 1970s. He theorized that near a black hole's event horizon, pairs of virtual particles and antiparticles are constantly being created and annihilated. These pairs arise due to quantum fluctuations, where one particle has positive energy and the other negative energy. Normally, these pairs would annihilate each other almost immediately. However, when this process occurs near a black hole's event horizon, one particle of the pair may fall into the black hole, while its counterpart, having received energy from the black hole's gravitational field, escapes into space. This escaping particle effectively constitutes Hawking radiation, which appears as thermal radiation emitted by the black hole. The emission of Hawking radiation allows black holes to adhere to the laws of thermodynamics by increasing their entropy. Over immense time scales, this radiation leads to a gradual loss of mass for the black hole. As more energy is radiated away, the black hole's mass diminishes until it eventually evaporates completely, a process that would culminate in a spectacular explosion if the black hole's mass were sufficiently small. This remarkable insight not only reconciles the behavior of black holes with fundamental physical laws but also offers a window into their eventual fate. By emitting Hawking radiation, black holes may eventually dissipate into the universe, leaving behind only their legacy of radiation and an altered cosmic landscape. This concept underscores the profound interplay between quantum mechanics, general relativity, and thermodynamics in understanding the most extreme objects in the universe. Time, that elusive dimension that dictates the flow of events from past to future, appears to possess an inherent directionality that aligns with our everyday experience and scientific understanding. While the concept of time running backward is intriguing and not entirely ruled out, several compelling indicators strongly suggest that time moves inexorably forward. Firstly, the thermodynamic arrow of time, grounded in the second law of thermodynamics, asserts that entropy within a closed system tends to increase over time. Entropy reflects the measure of disorder or randomness within a system. For instance, a broken cup on the floor represents an increase in entropy, It's a state of higher disorder compared to the cup intact on the table. The spontaneous reversal of such disorder to a state of lower entropy, where the cup magically reassembles itself, is fundamentally improbable. This irreversibility underscores the forward flow of time as dictated by the increase in entropy. Secondly, the psychological arrow of time correlates with human perception and memory. We remember past events that have already occurred but cannot recall future events that are yet to happen. Our subjective experience of time's passage is inherently tied to our ability to recall the past but not anticipate the future with the same certainty. This psychological asymmetry further reinforces the notion that time moves forward in a linear fashion. Lastly, the cosmological arrow of time is intertwined with the expansion of the universe. As the universe expands, entropy increases, analogous to the thermodynamic arrow of time. The evolution of the universe from a highly ordered state, such as the Big Bang, to increasingly disordered states reflects this cosmic trend. While theories entertain the possibility of the universe eventually contracting and reversing its expansion, intelligent beings like us can only exist and observe within conditions where entropy increases. The continuous expansion and increasing entropy serve as a cosmological backdrop that aligns with our perception of time moving forward. In conclusion, while the hypothetical scenario of time reversing remains a fascinating concept explored in physics and cosmology, the thermodynamic, psychological, and cosmological arrows of time collectively point toward an irreversible flow from past to future. These indicators underscore our understanding of time as a directional progression that defines our existence and perception within the universe. In addition to gravity, which is familiar to us as the force that keeps our feet on the ground, the universe operates with three other fundamental forces that govern the interactions between particles. The first of these forces is the electromagnetic force, which manifests in everyday experiences such as magnets attracting or repelling each other, or when we charge our electronic devices. This force acts on particles with electric charges, like electrons and quarks. Similar to how opposite poles of a magnet attract while like poles repel, electromagnetic force is responsible for binding electrons to atomic nuclei and governing chemical interactions. Despite being vastly stronger than gravity at the atomic level, it diminishes significantly over larger distances. The second fundamental force is the weak nuclear force, known for its role in radioactive decay. Unlike electromagnetic force, weak nuclear force operates over extremely short distances within atomic nuclei. At higher energies, this force can become as potent as electromagnetic force, influencing processes crucial to understanding the behavior of subatomic particles. Lastly, there's the strong nuclear force, which binds protons and neutrons together within an atomic nucleus, as well as the quarks that constitute these particles. Unlike electromagnetic and weak nuclear forces, strong nuclear force diminishes at higher energies. However, at incredibly high energy levels known as grand unification energy, all three forces, electromagnetic, weak nuclear, and strong nuclear, were once united as different facets of a singular force. This concept is foundational in theories about the early universe and its formation. In summary, beyond the omnipresent force of gravity, the electromagnetic, weak nuclear, and strong nuclear forces govern the interactions and behaviors of particles across the universe, from the atomic scale to the fundamental constituents of matter. Understanding these forces is essential to comprehending the intricate workings of the cosmos and the forces that have shaped its evolution since its inception. Although scientists widely accept the Big Bang theory as the origin of the universe, the precise mechanics of this cataclysmic event remain a subject of intense investigation and debate. The Big Bang theory posits that the universe began from an infinitely dense and hot state, expanding rapidly from a singularity. This expansion continues to this day, with the universe still growing and evolving. The hot Big Bang model describes how the universe started from a point of zero size and infinite density. As the universe expanded, it cooled, allowing fundamental particles to form and eventually come together to create atoms. In the first moments of expansion, the universe underwent rapid changes where basic forces and particles assumed their current forms. This early phase also facilitated the formation of the first elements, such as hydrogen and helium, which are prevalent throughout the universe today. Furthermore, as the universe continued to expand and cool, gravitational forces acted on denser regions of matter, leading to the formation of galaxies and clusters of galaxies. Within these structures, gravitational interactions caused clouds of gas to collapse, initiating nuclear fusion processes that fueled the birth of stars. The life and death cycles of stars then played a crucial role in enriching the universe with heavier elements, which were subsequently recycled into new generations of stars and planets. However, alternative theories like the inflationary model offer additional perspectives on the universe's early moments. According to this model, the universe underwent an extremely rapid expansion phase driven by a rapid increase in energy density. This inflationary period would have caused the universe to expand exponentially, smoothing out irregularities and setting the stage for the formation of the structures we observe today. While these models provide valuable insights into the origin and evolution of the universe, significant questions remain. How did the initial conditions that led to the Big Bang come about? What triggered inflationary expansion, and how did the fundamental forces of nature emerge from this early state? These questions continue to drive scientific inquiry and exploration into the deepest mysteries of our universe's birth and evolution. Physicists have long sought a unified theory that seamlessly combines two foundational pillars of modern physics: general relativity and quantum mechanics. General relativity, formulated by Einstein, elegantly describes gravity as the curvature of spacetime caused by mass and energy, providing insights into the behavior of large-scale phenomena like planets and galaxies. On the other hand, quantum mechanics delves into the microscopic world of subatomic particles, explaining their behaviors and interactions through probabilistic wave functions. Despite their individual successes, attempts to merge these theories into a single, cohesive framework, dubbed the theory of everything, have encountered significant hurdles. One major obstacle arises from the mathematical inconsistencies when trying to apply quantum mechanics to the curved spacetime described by general relativity. Quantum equations often yield infinities, indicating a breakdown in the predictive power of the theory. For instance, attempts to calculate the curvature of spacetime using quantum principles can lead to results that diverge to infinity, contradicting observed reality where such infinities do not manifest. To reconcile these discrepancies, physicists have explored various theoretical approaches, including string theory and loop quantum gravity. String theory posits that fundamental particles are not point-like entities but rather tiny vibrating strings of energy. This theory attempts to unify all fundamental forces of nature, including gravity, within a single theoretical framework. Loop quantum gravity, on the other hand, seeks to quantize spacetime itself, treating spacetime as discrete and granular rather than continuous, thereby potentially avoiding the infinities encountered in traditional approaches. Another challenge stems from quantum field theory's prediction that even seemingly empty space is teeming with virtual particles that pop in and out of existence due to quantum fluctuations. These virtual particles pose a conceptual challenge when trying to integrate them into the framework of general relativity. The energy associated with these virtual particles, if considered in the context of general relativity, would imply an infinite mass density across the universe, contradicting the observable universe's stable configuration. Moreover, Einstein's famous equation, E=mc², suggests that energy and mass are equivalent, implying that infinite energy would correspond to infinite mass. This scenario raises the specter of a universe collapsing under its own gravitational pull, potentially leading to a singular state akin to a black hole. Thus, while general relativity and quantum mechanics have each provided profound insights into different aspects of the universe, their unification remains an elusive goal. The quest for a unified theory of everything continues to drive theoretical physics, pushing the boundaries of human understanding in pursuit of a comprehensive framework that can describe all fundamental forces and particles in the universe. Physics, often depicted as a realm of daunting equations and abstract theories, holds within it the keys to unraveling the deepest mysteries of our universe. While its complexities may initially deter exploration, delving into physics unveils a world governed by elegant laws and principles that shape everything from the tiniest particles to the vast expanses of space and time. At its heart, physics offers us a glimpse into the fundamental nature of reality. From Isaac Newton's timeless laws of motion, which explain the motion of everyday objects with remarkable precision, to Albert Einstein's revolutionary theory of relativity, which transformed our understanding of gravity and space-time, these theories provide a framework that transcends mere observation. They allow us to predict, understand, and marvel at phenomena ranging from the motion of planets to the bending of light by massive objects. Even as quantum mechanics delves into the bizarre behavior of particles at microscopic scales, challenging our intuitive understanding of reality, it underscores the profound interconnectedness of all things. Concepts like quantum entanglement and uncertainty reveal a universe where particles can instantaneously influence each other across vast distances, suggesting a deeper unity underlying the diversity of nature. Moreover, physics encourages us to question assumptions and explore the limits of human knowledge. It invites us to confront paradoxes and mysteries that defy our everyday experience, pushing the boundaries of what we thought possible. Through this exploration, we not only expand our scientific understanding but also cultivate a sense of wonder and curiosity about the universe. Beyond its scientific significance, physics enriches our philosophical and cultural perspectives. It prompts us to contemplate the origins of the cosmos, the nature of time, and the possibility of parallel universes. These contemplations invite us to reflect on our place in the cosmos and the interconnectedness of humanity with the vastness of space. To fully appreciate the beauty and complexity of physics is to embark on a journey of discovery and enlightenment. It is an invitation to engage deeply with the wonders of the universe and to embrace a lifelong pursuit of knowledge and understanding. As we delve into the mysteries of physics, we not only gain insights into the natural world but also nurture a spirit of inquiry and appreciation for the elegance of scientific inquiry. In conclusion, let us embrace the challenge and excitement of exploring physics together. Whether you are a seasoned enthusiast or new to the wonders of the cosmos, I invite you to join me on this journey. Let's engage in discussions, share our thoughts and questions, and foster a community of curiosity and learning. Your comments, suggestions, likes, shares, and subscriptions are not just actions but contributions to building a community of knowledge seekers. Together, we can expand our horizons, deepen our understanding, and reach a wider audience eager to explore the mysteries of the universe. Thank you for joining us today, and until next time, let's continue to listen, stay curious, and seek wisdom. The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Albert Einstein.